Welcome to the 6th lecture of week 2. In this lecture, we will solve some numerical problems based on the equations for the homogenized properties that we derived so far. The first problem relates to density. So, here it says that we performed burn-off test of composite. So, when we do a burn-off test, basically the resin part or the matrix part is burnt off, and then we are left with the fiber. So, there is an empty crucible which weighs this much, and then when we put the actual composite sample in that crucible, the weight that we get is this, and after burning off, when the resin goes out, the rest of the fiber and crucible weighs this, and we have been given the density of fiber, density of matrix. Our job is to find out the density of composite, fiber volume fractions and fiber weight fraction. So, let us say W0, that is crucible weight is 10.1528 gram, that is what we are given, and then we are given W0 plus WC. So, W0 is crucible weight and WC is the weight of the composite. And that weight is 10.5219 gram, and we are also given W0 plus WF, with WF being the fiber weight, and that weight is 10.3221 gram. So, if I subtract this W0 from this, we will get the composite weight. So, composite weight is going to be 10.5219 minus 10.1528 gram, and that weight is found to be 0.3691 gram. Similarly, if I want to find out the fiber weight is, if I subtract the crucible weight from this quantity, then we get the fiber weight, and that is 10.3221 minus 10.1528 gram, and the quantity that we get is 0.1693 gram. Now, we have to find out the matrix weight. So, we know the weight of the composite. So, from the weight of the composite, if I just subtract the weight of the fiber, we get the matrix weight. So, weight of the matrix is equal to weight of composite minus weight of fiber, and if we do that, the result that we get is 0.1998 gram. Now, from these weights we can find out the weight fraction directly, and to find out the weight fraction, all we have to do is weight fraction of fiber is equal to weight of the fiber divided by weight of the fiber plus weight of the matrix, and this is nothing but weight of the composite, which we already have. So, if I divide this quantity 0.1693 by the weight of the composite, which is this, we can find out the weight fraction of composite. To find out the volume fraction of composite, I need the volumes. So, we have been given the density and the weight we have calculated. So, we can find out the volumes also. So, volume of matrix can be found out as weight of the matrix divided by the density of the matrix, and that is found to be 0.1665 milliliter. Similarly, the volume of the fiber is weight of the fiber divided by the density of the fiber, and that is found to be 0.06772 milliliter, 0.06772 0.72 milliliter. So, with this we can find out the fiber volume fraction, which is volume of fiber divided by volume of fiber plus volume of matrix, and that comes out to be 0.29. And we can find out the matrix volume fraction capital Vm, and that is small vm, that means volume of matrix, by the composite volume, that is volume of matrix plus volume of fiber, and if we do that, the result that we get is 0.71. Now, we have the constituent densities and the volume fractions. So, we can find out the density of composite rho c as a weighted combination of the densities based on what we derived at the beginning of this week, and that is found out to be 1.578 gram per milliliter. So, this solves the first problem. The second problem is related to E2. So, we have been given for a composite lamina the fiber elastic modulus along direction 2, matrix elastic modulus, and the individual Poisson ratio for the Poisson ratio for matrix, and Vf, that means the volume fraction of composite, and we are to determine E2 by the strength of material based approach as well as the Hall-Pin-Say relationship. So, for strength of material based approach, we can find it out as this. We know that 1 by E2 is equal to Vf by E2f plus Vm by Em, and we can just put the numbers here. So, 1 by E2f, E2 remains as it is, this is our unknown. Vf we have been given, that is 0.65, and E2f is 14.8 GPa plus Vm. So, Vm is, it is two phase material, there is only matrix and fiber. So, 1 minus Vf, which is 0.35. So, here we have 0.35, and Em is given to us 3.45 GPa. So, if you solve it, after solving we can find out E2, and that is found to be 7.56 GPa. Now, we have been asked to solve this same problem using Hall-Pin-Say relations also, and considering xi 1 to be 1. So, if xi 1 is equal to 1, then eta 1 becomes, as we know, the formula is E2f minus Em divided by E2f plus xi 1 into Em, and if we put all the numbers here, 14.8 minus 3.45 divided by 14.8 plus 3.45, because xi 1 is equal to 1, this gives eta 1 as 0.622. Now, we can write the expression for E2, and that expression is E2 multiplied by 1 plus xi 1 eta 1 Vf divided by 1 minus eta 1 Vf. Eta 1 we have already found out. So, if we put all the values, the value that we get is 8.133 GPa. So, these are the two values obtained from the two different approaches. Next question says, we have a composite and we have been given the longitudinal modulus of their constituents, and the fiber volume fraction is given 0.5, So, initially the composite is made of glass fiber and matrix. Now, the glass fiber fraction was kept to be 0.5, the volume fraction. Now, the question is, say we want to replace some of the glass fibers by carbon fibers, but keeping the total volume fraction of carbon fiber and the glass fiber to be same, and by doing that I want to double the elastic modulus along direction 1. So, to do that, how much of what fraction of carbon fiber I should put, or what would be the fraction of carbon fiber in that new composite. So, to do that, let us find out the elastic modulus before adding the carbon fiber. So, E1 we have been given Vf is equal to 0.5 and naturally Vm becomes 1 minus Vf and that is also 0.5. So, E1 elastic modulus along direction 1 is Ef multiplied by Eg. So, for this glass fiber the elastic modulus is 70 GPa. Generally glass fibers have elastic modulus same in both the directions, and here anyway it is given for the direction 1 only. So, this is what we have, and if we put everything here we get 0.5 into 70 here multiplied by 0.5 into 5. So, the our elastic modulus of this composite before adding carbon fiber was 37.5 GPa. Now, we want to replace part of the glass by carbon. So, once we do that, the glass fiber is going to reduce in volume. So, it will have a new volume fraction and carbon fiber will have some volume fraction. So, the reduction in the glass fiber volume fraction would be compensated by carbon fiber volume fraction. So, let us say that in that new composite the glass fiber volume fraction is Vg and carbon fiber volume fraction is Vc. Now, because the total volume fraction of the fiber remains unchanged, so that is equal to Vf is equal to 0.5. So, we can write Vg as (0.5) minus Vc. So, now we have a composite which is made of 3 different materials: glass fiber, carbon fiber and the matrix. So, we can extend whatever we had for the two phase material. So, now we extending that we can write E1 is equal to V1 multiplied by Vm multiplied by Em plus Vg multiplied by Eg plus Vc multiplied by Ec, and that should have our desired Young modulus, and the desired elastic modulus is nothing but twice of what we already have. So, that is 2 multiplied by 37.5. Now, here we have Vm known to me which is 0.5, Em is given to us which is 5 plus Vg is 0.5 minus Vc, and that is going to be multiplied by Eg which is 70 plus Vc is something which I do not know, that has to be figured out, and Ec is 300. So, it is 300 multiplied by Vc and this is equal to 75. So, now we can solve for Vc and we can get our desired volume fraction of carbon fiber. So, by solving we get 0.163. So, we should replace glass by carbon in such a way that the volume fraction of carbon becomes 0.163, and if we do that the resulting elastic modulus would become 75. So, carbon fiber has much higher elastic modulus as compared to glass fiber, that is why this small volume is going to cause this much of change in elastic modulus. Next question says, by using Hall-Pin-Shai relationship we have to find out shear modulus of a glass epoxy composite with a 70% fiber volume fraction, and we have been given the shear modulus of glass and epoxy as 35.42 GPa and 1.308 GPa, and let us assume that the fibers are circular and are packed in a square array. Next we will make another assumption for this fiber arrangement, then we will assume that the fibers are rectangular and with the ratio of longer to shorter dimension being so the longer to shorter dimension being 2 by 1, which is missed here, and the longer dimension is along the load direction. Now, to solve it using with the first assumption, that is they are circular and packed in a square array. So, in that case xi 2 has to be considered to be 1, as we have seen before. So, this is for circular fiber. If xi 2 is equal to 1, then eta 2 is equal to, as we know, this is G 1 2 fiber minus G of matrix divided by G 1 2 plus xi 2 multiplied by G m. So, we are already given G 1 2. So, G 1 2 f is 35.42 GPa and G m is 1.308 GPa. If that is the case, then eta 2 becomes 0.9288. Now, with that eta 2 we will find out G 1 2 now. With this expression G m multiplied by a fraction with the numerator as 1 plus xi 2 multiplied by eta 2 multiplied by V f divided by 1 minus eta 2 multiplied by V f. That gives us the value as 6.169 gigapascal. Now, next part of the problem says is that we have a rectangular fiber, rectangular cross section fiber, and that rectangular cross section fiber has B by A is equal to 2, with B being along the direction of the loading. So, B by A is equal to 2. So, B along the direction of loading. So, B along load direction. So, zeta 2 is now root 3 log E B by A, and if we evaluate that, so then xi 2 becomes 1.2, and with that xi 2 when we evaluate eta 2 using this same relation, then xi 2 turns out eta 2 turns out to be 0.922. So, there is no significant change in eta 2 based on the arrangement. Now, we can find out G 1 2, and if we find out G 1 2, this becomes 6.54 GPa. So, with circular fiber G 1 2 was this, and with square fiber this is this. Now, if we want to find out the same thing, although it is not mentioned in the question. So, say you want to find out the same thing using the strength of material based approach. So, we can write SOM approach here. We are doing it, although it is not mentioned in the question, but just to get an idea. If we do that, then using the formula 1 by G 1 2 is equal to V f multiplied by G 1 2 f plus V m Vm divided by G12F plus Vm divided by Gm, we get G12 as 4.014 GPa. So, what we are getting from the strength of material based approach is quite less than what we get from this semi empirical approach. Now, the next question is we have to find the longitudinal Young's modulus of a glass epoxy lamina with 70 fiber volume fraction, 70% fiber volume fraction, and we use the equations obtained using the elasticity model, and elastic modulus of glass and epoxy are given to us and Poisson's ratios are given to us. So, for that this would give us an idea of how much over or underestimation we do when we use mechanics of material based approach. So, we have Vf is equal to 0.7. So, naturally Vm is equal to 1 minus Vf and that is equal to 0.3. Em is given to us and that is 3.4 GPa and E1F is 85 GPa. Nu 1 to F is 0.2 and nu M is 0.3. Now, E1 as per the strength of material based approach, if we want to find out first. So, strength of material based approach, that is Vf into E1F plus Vm into Em, and what we get is 60.52 GPa. Now, say we want to find it out using the elasticity based approach. So, elasticity based approach, we have seen that it comes with a formula which has the first part same as what we have from the strength of material based approach, and then one fraction, and in that fraction in the denominator we have something called H, and then in the numerator we have something. So, if we do that, what we get is 60.52, that means whatever we are getting from the elasticity based approach divided by a fraction where we have H here, and in the numerator we have something. So, in the numerator what we get, I am directly writing that expression because that expression is quite long. So, please refer to that corresponding lecture and look at that expression, and then we have H here, and then that H was found out to be minus 142.17 into 10 to the power 9. Now, we can see here that H is a negative quantity. So, this is negative, and again this entire fraction is subtracted. So, this is finally going to be additive. So, after doing that, the value that we get is 60.53 GPa. So, this tells us that the strength of material based approach is quite accurate to what we get from the elasticity based approach. Now, the next problem is a similar problem, but we have to find out shear modulus here. So, for shear modulus, again the fiber volume fraction is same. So, fiber volume fraction is 0.7 and the matrix volume fraction is accordingly 0.3, and we will use what we learned from the theory of elasticity based approach, and as per that the relation was G12 is equal to Gm multiplied by Gm into 1 plus Vf plus Gm into 1 minus Vf. So, this is G1 to F, and then we have G1 to F multiplied by 1 minus Vm plus Gm, then we have 1 plus Vm. So, here G1 to F is given to us as 35.42 GPa and Gm is given to us as 1.308 GPa. Now, if we evaluate the expression by putting all these numbers, then finally, the value that we get is 6.169 GPa. So, if we look into the previous example that we did using the Hall-Pinchai equation and the strength of material based approach, this problem here also we can see that for circular fiber xi 2 is equal to 1, we got the same value here, and that is what we get here. But using the strength of material based approach, this value was quite underestimated. Now, again similar problem, but this involves Poisson's ratio. So, you have to find out the measure Poisson's ratio for a glass epoxy ply, and again Vf is given to be 0.7 and Vm is accordingly 0.3, and elastic moduli are given for glass and epoxy. We have to find out the Poisson's ratio. So, we have again V of E is equal to 0.7 and accordingly Vm comes to be 0.3, and we from the strength of material based approach, if we find it for the sake of comparison, nu 1 2 comes out to be nu 1 to F multiplied by Vf plus nu m multiplied by Vm. So, nu 1 to F is given as 0.2 and nu m is given as 0.3. So, with that the value that we get here is 0.23. Now, if we want to get the same thing using the elasticity based approach, then we have as per the formula the same thing that we get from the strength of material based approach plus one fraction, and in that fraction the denominator was same as the denominator that we had for the expression of the elastic modulus along direction 1. So, again in that fraction we have H, and in the numerator again we have a big expression. So, for that the numerator that we have, the final value of the numerator is 0.8767 into 10 to the power minus 9, and H as we calculated before also is minus 141.17 into 10 to the power 9. So, with that the value comes to be 0.2238. So, here we can see that the denominator is negative here, but finally that fraction is added. So, that is why this has a negative effect. That is why the nu 1 2 is going little down if I find out using the elasticity based approach as compared to the strength of material based approach. So, these were some of the numerical problems that gave us an idea about how the values turn out to be using different approaches, and how to use the different equations that we get using different approaches. In the next week, we will talk about the other challenges that composite has, that means the problems associated with anisotropy, and for that we will have to have this homogenized property with us. So, with that I would like to conclude this lecture and also conclude this week. Thank you.